Okay, so today's lesson is on 7.4b, solving using logs. Our content objective is to solve equations using logarithms, both logs or common logs and natural logs, log and ln. And our language objective is to use the correct terminology to describe how to solve using logs. So quick refresher, common log is our log base 10. So log base 10 of something would be a common log, which we just write as a log of x. So you don't actually write the 10, you just write log of x. And then we also have, which I don't believe we've explicitly talked about yet, but the natural log. Sorry, that's a log. And that is a log base e, or as you'd see it elsewhere, just ln. So ln means the natural log, so it just implies a log base e, but they use ln to represent it. A common log is a log base 10, but they just use a plain log to represent it. So let's talk about, I want to tie this into stuff we've been doing before. So I want us to, for our first example, solve with the following problem with logs. And we have 15 equals 3 to the x. So I'm going to do method 1 first because this is what we've been doing previously. So if I started with 15 equals 3 to the power of x, I'm going to write this in half so I leave room on the other side. I'm going to first rewrite as a log. So when I do that, I know this is the base, this is the power, this is the argument, so I end up with a log base 3 of 15 equals x. So again, I've isolated my variable, correct first step. Now to plug this into my calculator, since this is not an even number, there's nothing, 3 to any power does not give me 3 to a whole number power will not give me 15. So I'm going to rewrite using the change of base. So when I do that, I end up with log 15 over log 3 equals x, because I want to be able to enter this on my calculator, so I want to have a log that's on my calculator. Then I'm going to evaluate it. So I'll show you how to do this on a calculator today if you have not tried it on your own yet. But if I have this, I now can type in log of 15 divided by log of 3 equals 2.4649. So then I get x equals approximately 2.464, so on. So I'm going to round this to approximately 2.46 as my final answer. So that's our first method for using this. So we've done this before. That is an easy way to solve for logs. But there's another way you can think of this, or another way to solve this, that's going to bring you to the same spot, but in a slightly different way of thinking about it. So again, we're starting with 15 equals 3 to the x. So I'm going to, instead of rewriting it as a log base 3, I'm going to take the log of both sides. So step 1, take the log of both sides. So when I do that, I end up with log 15 equals log 3x. And again, I'm using just a log base 10 because that will be easier in the long run. So since I do the same thing to one side that I do to the other, the same way we've solved equations as long as you've been solving them, whatever you balance equations. But then I'm going to use my LOLs, laws of logs. I'm going to abbreviate it as LOLs to bring down my exponent. So now I have log 15 equals x log 3. And then I'm going to divide by log 3 on both sides. So I divide by log of 3. And look, I've ended up with log 15 over log 3 equals x. So now it's back to that same point where I evaluate, and I'm going to get the same answer, x equals approximately 2.46. So again, you end up with the same point, but there's two different ways of thinking about it. You can either rewrite it as a log, and then you just change your base, or take the log of both sides, and then use laws of logs and divide. So similar processes in either way, whichever way makes more sense to you is great. But you're going to have to be able to do that in different solving circumstances. So Another way we kind of have to think about, or that we have to think about logs, is as inverses of one another. So we've talked about this extensively, but I want to show you one thing we haven't quite talked about explicitly. So logarithms and exponentials, as we know, equations are inverses. Thus, they undo or cancel each other. So what that means, or the reason I'm bringing this up again, is because there's two different ways we can sort of visually see this play out. So if I have log base b of b to the x, it's just going to be x. So, because if you think about evaluating it, b to the what gives me b to the x, x would give me that value. Or you can think of it as these are canceling each other and you just end up with x equals x. So what I mean by that, if I had a common log of 10 squareds, it's an implied base of 10. 10 to the what gives me 10, it's going to be 2. It also works the other way. So if a log with the same base cancels that base, but if I have an exponent, so if I have b to the power of log b of x, this base and the log base here are going to cancel each other out and you're just left with x. So we'll use a natural log in this case. So if I had e to the ln of 5, those are going to cancel each other and you'd just be left with 5 because ln is a log base e. Those are inverse operations, exponents and logs, so they would cancel each other out. All right, so we've already been doing this, but I want to do one more quick example so that you can see how we can use these methods in application. So I'm going to flip the page for that. If you want to send me a quick email and tell me you're listening, send a little timestamp, that would be great. So send that email now. Okay, so you invested $1,000 in an account that earns 6% annual interest, compounded continuously. How long will it take to be worth, for the account to be worth $2,500? All right, so this is our application problem. So we're going to start using our growth and decay, or our PERT in this case, by setting up the equation. I know I'm using PERT because it says compounded continuously. Whenever it says compounding continuously, I know I'm using E. So I'm using VT equals PE to the RT. So if I plug that in, I know the final value I'm looking for is 2,500. I know the principal amount is 1,000. E is already a number. I leave it as E. 6%, I'm going to write as 0.06. And then there's a T because I'm solving for how long or the time that it will take to reach that value. So I'm solving for T. The variable I have is going to be in my exponent. So now, before I can solve for T, which is my value of my exponent, I have to isolate the base and the exponent. So my second step is going to be to isolate base and exponent, or the base and exponent. So when to do that, I'm going to divide both sides by 1,000. Those 1,000 cancel, and I'm left with 2.5 equals e to the 0.06 t. So I've isolated my base. This is where logs come into play. There's two ways we can think about it. We're going to isolate the exponent using logs. And I'll show you again both ways you can do that. If you wanted to imagine you took the ln of both sides, you'd end up with ln of 2.5 equals ln of e to the 0.06 t. Here, the ln and the e cancel each other, and you have ln of 2.5 equals 0.06 t. The other way you could think about it is you're going to rewrite this as a exponential equation. So this would become a log base e of 2.5 equals 0.06t, which I know log base e is just ln. So I end up at the same equation. ln of 2.5 equals 0.06t, or 0.06t if it helps you to write that 0 in front. Now I'm just trying to isolate t, or isolate the variable. So to isolate the variable, I'm going to divide both sides by its coefficient, 0.06. So I divide by 0.06 and I get ln of 2.5 over 0.06, or 0.06 equals t. And then I'm just going to evaluate with a calculator, or calculate it out with a calculator. So at this point, I'll plug this in here. I have ln of 2.5 divided by 0.06 is 15.27. So t equals approximately 15.27. So about, my answer for the original problem will be about 15.3 years. And that's my final answer. So answer. That's all for now. I will have you guys practice this some more in class, but make sure you write down any questions, comments, or concerns you have so we can go over them together.